If you are following from the previous video lecture, we have finished the case 1. Now we will move to case 2. So what is the case 2? The case 2 is if the point P is inside the solid sphere. Okay, so that means small r is going to be less than capital R. Okay, so let me show you diagrammatically. Suppose this is a point, this is center O. Okay, so we need to find out the gravitational potential and intensity at this point, say P. Okay, so this whole thing is, so as usual you know that this radius is capital R and this distance is small r. So this distance is small r and here small r is less than capital R. Now why the situation is now different? Now the situation is different because there will be different impact of potential due to different parts of the sphere. So at the point P, we are going to have two effects. If I can suppose, let us assume I am drawing one concentric sphere like this. Okay, so you can see that this point P is on the surface of a sphere whose radius is smaller. Is on the surface of a sphere whose radius is smaller. So that is one case. And another case is that at the point P there will be a gravitational effect due to this part. Okay, this part of the shell. Now this part is like a shell. So at the point P we are going to have two gravitational effects. What are the gravitational effect? One because of the sphere of radius smaller, because P is on the sphere of radius smaller. At the same time P will also be affected by the gravitational effects of the spherical shell of this portion, the red colored portion. Okay, so we will divide this thing into two parts. Okay, so we will call, say, first of all first thing we will call V1. I hope this color is okay. Let me choose some other color. Okay, we will choose this. Okay, fine. So we will say that the potential at P due to the whole solid sphere can be divided into two parts. Okay, so we will be writing like this: V equal to V1 plus V2. Okay, so what is V1 here? So where V1 is the potential due to the solid sphere of radius smaller. So this one. Okay, and V2 is a potential due to the remaining part of the sphere. Remaining part of the sphere means the red shaded region. Okay, the red shaded region is the remaining part of the sphere. So we will have to solve this problem into two parts. Okay, so let us start with that. So before proceeding, let us define a few simple things. First of all, let us assume that the total mass of the solid sphere is capital M. Therefore, mass density or mass per unit volume rho is given by mass per volume. Now you know that the radius of the sphere is capital R, so it will be 4 by 3 pi r cube rho. Now you can differentiate this thing with a solid spherical shell. In case of spherical shell, we took area, not volume. So this thing we have already discussed in class. So let us proceed with that. So this is our equation number, say 1. Okay. And let it be like this. Now let us find out the V1. What is V1? V1 we mention in blue color, and blue color means the solid sphere. So you know that. So therefore, potential at P due to the solid sphere of radius small r is given by, so V1. So you can, if you remember, just if in the case 1 we have derived the expression for potential due to a solid sphere, okay, at a point either on the surface of the sphere or outside the sphere. That expression was like this: G capital M by small r, if you remember. So we can simply write it as G into mass by small r. Okay. So here, if you want to find out what is a mass, because we have mass per unit volume is rho. Okay. Now what is a volume? So let me remove this. So it is G. So rho is equal to mass per volume. So mass will be equal to rho into volume. Fine. So it will be rho into volume by R. So minus G by small r. Rho into volume means 4 by 3 pi small r cube, because we are talking about this sphere. So this sphere has a volume of 4 by 3 pi r cube. So it is written as like this. So it is G. So you can see R, let's cancel. So it is like G 4 pi rho r square by 3. This is our V1. If you wish, you can put the value of rho here directly. So what I will be doing, so I will directly use the value of, so therefore implies V1 equal to G 4 pi r square by 3. If we know the value of rho is nothing but m by, from equation 4 by 3 pi r cube. This is from 1. If you remember, we have already done this, rho equal to this. Okay, so we will simplify it. We will try to simplify it. So minus g. While simplifying the things, don't make a rush. Just do it slowly without missing anything. So this is 4 pi. 4 pi gets cancelled. 3 gets cancelled. So we simply have g m by r cube into small r square. So I'm putting it like this because these things are constant. Only thing that is going to change is r square. So this is our v1. So let us save it and let us name it as equation number 2. Now we will proceed for the next section, that is to find out the value of v2. Okay, so now to find the value of now, so I will change my colors. So this is a color now. So to find the value of v2. Okay, so what was v2? If you remember, v2 is that potential at the point P due to this shaded region. This is red colored region. What is the speciality of this? This is the remaining part of the sphere. Okay, so since our figure has got overlapped with so many things, so we will draw it again. So this is the sphere we have. So this is the point O, this is the point P. Okay, and we have already drawn one concentric sphere like this. Okay, and this is our capital R, this is our small r. Fine. So now the interesting thing is that to find out the potential at the point P, okay, let us assume, we will be assuming one thin shell like this. One thin shell like this. And what is the location of this shell? It is lying between the point P and the surface. Okay, and this is the shell we have, and this is a spherical shell, and I have considered it in the remaining part of the sphere. Okay, and what is the speciality of this shell? This shell is of radius x, and this shell is of thickness dx. Okay, and all of them have the same center. That is why we are always saying that it is a concentric. Okay, and now if you see, the point P is inside this spherical shell. If you can remember, there was a case of spherical shell where we derived the potential of the gravitation potential due to a spherical shell inside it, at a point inside it. Okay, so we are almost doing something similar to that. So in this case, what we'll be doing, so instead of finding out the total potential due to this whole portion, first of all, what we will be doing, we will find out the potential only for this portion, only for this thick shell. Okay, and then we will integrate it and we will find it for the whole shell. Okay, so for that, what we will be doing, so let us write down potential at P due to the thin spherical shell where x is like is. Okay, so the simplest way to proceed is, say dv2 is equal to, again the same thing, g mass by This term it is how much? X. Now minus G by X. Now if I talk about mass, mass is nothing but rho into is equal to rho into volume. So here again rho into volume. What is the volume here? Now volume, we need the volume of this thick shell. As you can see, I'm drawing with some black ring. Okay, we need the volume of this thick shell. So if you know, the surface area of the shell is 4 pi x square. If you multiply it by dx, it will give you the volume of the shell. So it is 4 pi x square dx. This is the, so rho into volume, this gives you the mass of the thick shell. Now, as a result, we will just simplify it and it comes out to be G4 pi rho G4 pi rho x dx. So this is our dV2. So we can further put the value of, implies dV2 is equal to, we can further put the value of 4 pi, rho means capital M by 4 by 3 pi r cube. This is from equation 1 and this is x dx. So 4 pi gets cancelled. So I will try to simplify it, 3 by r cube x dx. So this is dv2. Okay, so try to understand this thing. This thing is a potential at the point P due to this thick shell of, due to this thin shell of thickness dx and radius x. Now if I want to get for this whole thing, I will have to integrate it. If I integrate the result for the thin shell, I will get the potential for this whole shell. So therefore, potential at P due to the remaining portion of the sphere is V2 is equal to 0 to V2 dV2. So in our case, it is dV2 is nothing but minus 3gm by r cube x dx. Okay, now we need the value of lower limit and upper limit of x. Okay, so if you look at this figure, so x starts from here, so this is smaller, and x goes maximum up to here. This is capital R. So this is x and this is smaller limit, lower limit of x. This is the upper limit of x. So lower limit of x is smaller, upper limit of x is capital R. So smaller and this is capital R. So we have minus 3g capital M by r cube outside, small r2 capital R x dx minus 3gm by r cube x square by 2. It goes from again small r to capital R, and therefore 3gm, I will take the 2 outside, so 2 r cube, so it will be capital R square minus small r square. Okay, so this is our V2. Therefore, the total potential. So how to find out? Therefore, total potential at P due to the whole solid sphere is V equal to V1 plus V2. Okay, so we will find out what is V1. We will go back. What is our V1? V1 is Gm by R cube into small r square. So V1 is minus Gm by R cube into small r square minus V. So plus what is our V2? Minus 3Gm minus 3Gm by 2 r square. Sorry, r cube into r square minus small r square into capital R square minus small r square. So we will simplify it. Gm by r cube into small r square minus 3Gm by 2 r cube into capital R square minus small r square. Okay, so we can simply take what I will do, I will put a 3 here, so it is 3Gm and 3 below also. We can do some modification like this. So 3Gm by 2r cube capital R square minus small r square. So we have minus, so can I take 3Gm by r cube outside? Okay, so what will we will be left with? R square by 3 so it will be r square by 2 minus minus plus 2. So since we have already taken the minus outside, it will be plus, and this will be minus. Okay, so minus 3Gm by r cube. So let me take the LCM. So it will be 2r square plus 3 capital R square minus 3 small r square. This is how it goes. Then 3Gm by r cube. So we have 6 here. So 3 capital R square minus small r square. So this 3 2s are 6. So we have Gm by r cube 2 to 3 r square minus small r square. So this is our total V. So from this we can further find out, therefore fill intensity at P due to the solid sphere with small r, and r is given by E vector equal to nebula vector v. So minus nebula vector, what is our v now? V is minus gm by 2 r cube, 3r square minus small r square. Okay, so we have nebula vector gm by 2r cube, 3r square minus so if you simplify further, gm by 2 r cube nebula vector 3 r square minus small r square, so it will finally come out to be gm by 2 r cube nebula vector 3 r square minus nebula vector r square. So this part is constant, it will definitely become 0. So gm by 2 r cube, so it will be nebula vector r square. So finally it will come out to be, you can check out the calculation in detail. So it will be r cap. So this will be your electric field, gravitational intensity at the point P due to the solid sphere, where the point is inside the solid sphere. So there are some graphical representation for this, which I have already mentioned in the note. You can check it and you can match it with the expression that you have obtained.